Section: Introduction. We're here to talk about transformers, a type of neural network architecture that has had a significant impact on machine learning. These models have been successful in various fields, such as natural language processing, time series forecasting, and computer vision, thanks to their scalability and efficient use of modern hardware designed for parallel computing. However, as these models grow larger and more complex, the challenges of training them, such as the exponential increase in parameters and computational requirements, become more daunting. This often means that only researchers with access to substantial GPU resources can achieve top-tier results. To address these challenges, we're exploring a different approach, merging multiple transformer models into one while maintaining their unique capabilities. This approach has several benefits. Firstly, it can improve performance by combining the strengths of individual models. Secondly, it can reduce complexity during inference, as querying one model is simpler and less computationally intensive than querying multiple models in an ensemble. Lastly, it eliminates the need to train models from scratch, as we can leverage existing public models. A simple way to merge models is to average their weight matrices, a method known as vanilla fusion. However, this method doesn't account for potential misalignments between the parameter matrices, which can occur when neurons at the same positions in different models encode different information. To address this, we propose using optimal transport fusion, OT fusion, which aligns the weight matrices before merging them. This ensures that the merged model effectively integrates the knowledge and capabilities of the individual models, rather than just averaging the weights. OT fusion can also merge models of different sizes, which vanilla fusion cannot do. This is important because there are many pre-trained models of different sizes available. OT fusion has proven effective for merging fully connected, convolutional, and recurrent neural networks, significantly outperforming vanilla fusion. However, the layer-wise procedure of OT fusion doesn't fit well with modern architectural design, which includes constant residual streams, normalization layers, and attention operations. Therefore, our main goal is to develop techniques that bridge these gaps and successfully generalize fusion to transformer-based architectures. Our contributions include a detailed analysis of the unique architectural components in transformers to determine the best way to fuse them across different models. We also found that, surprisingly, OT fusion based on a hard alignment underperforms in this context, and that soft alignment plays a key role in successful one-shot fusion. We demonstrate the effectiveness of our approach through extensive experimentation involving the fusion and fine-tuning of vision transformers, VITs, across multiple datasets, as well as BERT models for natural language tasks. We consistently outperform the original models across tasks and datasets, while significantly reducing computational and storage costs. In summary, our research represents a significant step forward in advancing model fusion techniques, delivering enhanced performance and efficiency for modern transformer-based architectures. The idea of combining multiple models has been a long-standing concept in machine learning, with the aim of boosting model performance by capitalizing on the unique strengths of each model while mitigating their individual limitations. In recent years, model fusion has gained significant traction in the machine learning community. This approach focuses on building better model combination methods that account for the network structure and its inherent symmetries. We propose a novel approach based on the optimal transport theory, which allows us to fuse pre-existing models in a one-shot fashion without requiring retraining. This approach outperforms vanilla fusion and has been successfully used for model compression and fusion of CNNs, residual networks, and multi-layer perceptrons. However, it does require the models to have the same depth. This limitation has been addressed to some extent by using cross-layer alignment, a method that balances the number of layers of the neural network before applying layer-wise model fusion. Other researchers have built on top of OT fusion, generalizing the work as a graph matching task, and taking into account the second-order similarity of model weights instead of linear alignment. The interest in model fusion is growing in the research community, and recent efforts on the topic have shown theoretical insights on fusion, extensions of previous algorithms to new network topologies, and fusion of models performing different tasks. Section Summary. Transformers have had a significant impact on machine learning, excelling in various domains due to their scalability and efficient use of hardware. To address the challenges of training large transformer models, we propose merging multiple models into a single entity using optimal transport fusion, OT fusion, which aligns weight matrices before fusion to preserve meaningful information. Our approach outperforms vanilla fusion, VF, and has been successfully applied to vision transformers, VITs, and BERT models, achieving enhanced performance and efficiency. Section: Fusion with a focus on transformers. We're looking at how to combine different transformer models that have been trained on the same data but fine-tuned differently. These models are close enough in their parameter space that we can simply average their parameters to fuse them, which improves performance. However, we're more interested in fusing transformer networks that are quite different in their parameter spaces and characteristics. This could be because they started with different initial settings, were trained on different batches of data, or have different sizes, among other reasons. This is the first work, as far as we know, that aims to fuse transformer architectures by aligning their weights. We use a method called optimal transport, OT, to compare probability distributions effectively. This method is used in machine learning for tasks like generative modeling, class incremental learning, and model compression. OT finds a transport map, TM, which shows how much of source distribution should be moved to a destination distribution to align the two. This alignment can be strict, where the TM is a permutation matrix and the solution to the Earth mover's distance problem, or it can be relaxed, which is solved with the Sinkhorn-Knapp algorithm. The degree of alignment is controlled by a regularization parameter, where lower values result in stricter alignment. We apply this theory to align networks layer by layer, using either weights or activations as the underlying distributions. After aligning one or more models to an anchor model, we then average them. For a given layer of the model, we multiply the transpose of the TM of the previous layer with the weight matrix of the current layer. We then align the current layer by multiplying it with the TM of the current layer. With a modular architecture like the transformer, it makes sense to use a divide-and-conquer approach to develop a fusion algorithm. We first break down the architecture into its simplest building block, fully connected layers, that can be fused using the OT fusion strategy. The challenge is how to effectively connect these building blocks, especially if they're different, and how to reconstruct a fully fused transformer while maintaining the consistency of the fused blocks. We'll guide our discussion with a transport flow perspective, which allows for an intuitive and effective concatenation of blocks of any type, and can be applied to any architecture. In the typical OT fusion application, the TM of the previous layer is simply passed to the next layer. However, in more complex architectures, the incoming TM of a layer can depend on multiple TMs. To formalize and visualize this flow of TMs, we present the transportation map flow graph. This graph uses rectangles to represent the neural network layers, red nodes to represent any non-learnable computations or permutations inside the network, and edges to represent the propagation of the TMs. Layers have exactly one incoming and one outgoing edge. Computation nodes always have multiple incoming edges and one outgoing edge, where the outgoing TM must depend on the incoming TMs. The most challenging aspect of applying OT fusion to complex architectures is determining the ideal strategy for propagating TMs through red nodes. In residual connections, the outputs of a current layer and a residual layer are summed up. The TMs coming from these two layers will be different, therefore the ideal TM flow strategy has to be determined. We explored three heuristics to calculate a weighting vector, where each entry scales the corresponding rows of the TMs. After obtaining the weighting vector, we compute the weighted average. We found that for plane averaging, we set each entry to 0.5. This heuristic does not depend on activations and can therefore be used even in the case of weight-based alignment. However, it assumes that the residual and the current layer TM are of equal importance when aligning the subsequent layer. To alleviate the equal contribution constraint from the averaging method, we compute a weighting factor using the activations of the anchor model over a batch of samples. This carries information about the importance of the current and the residual branch in the anchor model. As opposed to the weighted scalar method, here, we calculate a weight vector where each entry weighs each residual connection separately. We note that in the case of hard alignment, these methods perform worse than averaging. Section summary. The paper discusses the fusion of transformer models by aligning their weights using optimal transport, OT. The authors propose a method called OT fusion, which aligns the weights of different transformer networks, even if they are diverse in nature, such as having different initializations or sizes. They introduce the concept of a transportation map flow graph to visualize the flow of transport maps, TMs, through complex architectures, and explore different strategies for propagating TMs through residual connections. Section: Multi-head attention. Let's delve into the complexities of the multi-head attention mechanism. This mechanism presents several challenges when it comes to tensor mapping, TM, flow. We need to determine the incoming TMs for the weight matrices W-Q, W-K, and W-V. We also need to figure out which TM is propagated to the output weight matrix W-O. And finally, we need to handle attention with multiple heads. The first challenge can be addressed using the TM flow graph. We can simply use the TM from the previous layer for each of the weight matrices W-Q, W-K, and W-V. This approach works even when dealing with multiple heads. However, determining the incoming TM of the output weight matrix W-O is more complex because it depends on the outgoing TMs of the weight matrices W-Q, W-K, and W-V. If we restrict both TMs of the weight matrices W-K and W-Q to be equal permutation matrices, which means a hard alignment with T_Q equals T_K equals T_QK, we find that the permutation matrices cancel each other out inside the softmax function. This indicates that the product in the softmax function is not affected by the alignment and that the TMs of the weight matrices W-K and W-Q do not need to be propagated. Therefore, only the outgoing TM of the weight matrix W-V is propagated to the output weight matrix W-O. We also explore the possibility of relaxing the constraint of equal TMs for the weight matrices W-K and W-Q and the propagation of T_V in the context of soft alignment. We then address the fusion strategy for the multi-head architecture. Attention heads are permutation invariant with respect to other heads, which means that one head can be swapped with another without disrupting the attention mechanism structure. Moreover, there is no inherent one-to-one correspondence between the heads of different transformer models. To incorporate these observations into our algorithm, we propose cross-head alignment. During cross-head alignment, the weight matrices W_I_Q, W_I_K, and W_I_V are concatenated across the output dimension to form three combined weight matrices. OT fusion can then be directly applied to the concatenated matrices, and T_V can be propagated to the output weight matrix W-O. Next, we discuss layer normalization, embeddings, and bias. The layer normalization is a learnable parameter of the neural network and must be fused. It contains only two parameters, alpha and beta, per input, and there are no interconnections between different inputs and outputs. Therefore, no TM needs to be computed for this layer. The parameters are only aligned with respect to the incoming TM, which is then propagated to the next layer. The vision transformer, VIT, embeddings fusion approach is best explained by its TM flow graph. For the concatenation, we note that the class token is only a small part of the full sequence. Therefore, it's more important to propagate the TM of the patch embeddings than the one for the class token. After concatenation, the positional embeddings are added. We note that the addition operation is the same as for residual connections, so we can use one of the three TM flow strategies from section 3. The bias is only connected to the output of a neural network layer, so we align it using the outgoing TM of the corresponding layer. We also discuss alignment strategies. We find that OT fusion works best when using the Earth Mover's Distance, EMD, solver, which computes permutation matrices as TMs. However, we don't want to limit the search space for optimal alignment to only permutation matrices, as this seems too restrictive for complex architectures. Therefore, we explore using the Synchrone algorithm and tuning the softness of the TM by optimizing over the Synchrone regularizer. We also compare weight-based and activation-based alignment strategies. The weight-based approach can be directly applied to transformers, while the activation-based strategy requires more consideration. Transformers operate on sequences of tokens, unlike simpler architectures that operate on one token at a time. In our activation-based algorithm, we treat every token of the sequence as a potential activation. In transformers, it's clear that not every token within a sequence contributes equally to an output. For example, in an image classification task with VITs, all information must have been moved into the class token by the end of the encoder chain, while the other tokens of the sequence will not contribute any more to the classification. We hypothesize that activation-based alignment performs best if it is performed using only the most important tokens in the sequence. Therefore, we explore filtering out the least relevant information. For datasets where images are centered, we propose window filtering, where only an n by n window of patches is selected for every image. Additionally, we explore what happens if only the class token is used to perform the activation-based alignment. Section Summary. The multi-head attention mechanism in transformers poses challenges in terms of determining the incoming and outgoing token matrices for each head. However, by using the TM flow graph, we can easily solve the first challenge by using the TM from the previous layer for each head. The second challenge of obtaining the outgoing token matrix for $BFW, $O is more complex, but if we constrain the token matrices of $BFW, $K and $BFW, $Q to be equal permutation matrices, we can observe that the permutation matrices cancel each other out inside the softmax, allowing only the outgoing token matrix of $BFW, $V to be propagated to $BFW, $O. Additionally, we propose cross-head alignment to handle the fusion strategy for the multi-head architecture, taking advantage of the permutation invariance property of attention heads and the lack of one-to-one correspondence between heads of different transformer models. Section. Experiments and results. We put our approach to the test using two well-known transformer-based models, VIT and BERT. Our goal was to see how well our fusion techniques performed in both image and natural language processing, NLP, domains. These models were chosen because they have the same encoder-only architecture, making them ideal for comparison. We ran our experiments on several popular image classification datasets, including CIFAR10, CIFAR100, Tiny ImageNet, and ImageNet 1K. We used Hugging Face for both implementing the VIT and accessing the datasets. In addition to image classification, we also demonstrated our fusion strategy on the BERT model for an NLP task. We trained multiple BERT models from scratch on a masked language modeling task using a subset of the Wikipedia dataset, which is publicly available on the Hugging Face Hub. We started by training individual models from scratch on each dataset until they reached their peak performance. To ensure diversity among the models, we initialized each one with different seed values and randomized the batches. This resulted in unique models that performed similarly but had a wide variety in their parameter space. This diversity posed a challenging fusion problem that required a non-trivial alignment strategy, effectively simulating a variety of other scenarios, such as models trained on different subsets of data. We then evaluated our proposed fusion strategies on the CIFAR10 dataset. We measured performance based on the one-shot capability, which is the performance of the fused model, without any retraining, on the same task and metric as the parent models. This capability is a good indicator of the fusion algorithm's ability to align and then fuse the parent models. The best fusion strategy identified on the CIFAR10 task was then applied to the other tasks and architectures. We also evaluated the effect of fine-tuning the fused model. The performance of the fine-tuned model was compared against the single parent models at their peak performance, their ensemble, and the VF model that also underwent a round of fine-tuning. Both our fused model and the VF model were optimized separately over a common set of reasonable hyperparameters. In our one-shot experiments, we found that a soft alignment strategy consistently outperformed hard alignment. The optimal strategy for handling the residual connections turned out to be the averaging policy. The best performance was achieved with our soft, activations-based fusion. We also conducted ablation studies to examine the effect of different OT fusion hyperparameter choices on the one-shot performance on the CIFAR10 dataset for two-model fusion. We found that soft alignment, which is more flexible, allowed for better performance retention. We also found that the optimal alignment is neither hard nor merely soft. Furthermore, soft alignment for the activations-based fusion was much more stable than hard alignment for different seeds of data. In conclusion, our experiments demonstrated the superior performance of our algorithm in comparison to VF, emphasizing its ability to facilitate more dependable knowledge transfer. Section Summary. The authors conducted experiments to evaluate the performance and robustness of their fusion techniques on transformer-based architectures, specifically VIT and BERT, in both image and NLP domains. They trained individual models on different datasets and initialized them with different seed values to ensure model diversity. The fusion strategies were assessed on the CIFAR10 dataset, and the optimal fusion strategy was then applied to other tasks and architectures. The authors found that their fusion methodologies outperformed a naive approach and preserved most of the capabilities of the individual models. Section: Fine-tuned performance. We're now going to discuss the final stage of our experiment, which involves fine-tuning the combined models. The performance and retraining curves of these models provide valuable insights into the effectiveness of our fusion algorithm. If even a single layer is problematic, it can significantly affect the one-shot performance. However, the ability of the combined model to quickly and efficiently regain the performance of the parent models gives us a deeper understanding of the fusion's quality throughout the entire architecture. We tested our fine-tuning results on widely used datasets like CIFAR100 and IMAGENET1K. We've included results on Tiny ImageNet in the appendix. We first applied our fusion approach to the vision transformers, VITs, trained on the CIFAR100 dataset. We optimized the combined model separately using a common set of hyperparameters, specifically a learning rate between 0.001 and 0.00001, and the number of epochs between 10 and 200. Our results showed that both our soft alignment strategies, using weights and activations-based alignment, were able to outperform the parent models. This performance improvement increased with the number of parent models, suggesting successful knowledge transfer to the combined model. Although the accuracy was lower than the ensemble performance, our approach didn't require additional computational resources, unlike ensemble models which increase in cost linearly with the number of models. We also tested our approach on the challenging ImageNet-1K dataset. The results were consistent with the CIFAR100 case, demonstrating the general applicability and scalability of our methods to larger models and more challenging datasets. However, even after fine-tuning, the Vision Fusion, VF, failed to achieve comparable accuracy, resulting in suboptimal performance. While our focus was on the vision application of the transformer architecture, our method is flexible and can be applied to the BERT model. Preliminary tests of our fusion strategy on the BERT model showed some differences compared to the VIT case, but the results were comparable to those previously discussed. Specifically, the combined and fine-tuned model outperformed both parent models and VF on a widely used benchmark. Unlike VF, our method can be applied directly to models of different sizes, heterogeneous fusion. We observed a consistent increase in test accuracy over the performance of the smaller anchor network, indicating successful knowledge transfer. This suggests that our method is an effective and efficient alternative to knowledge distillation. Our fusion methodology for transformer models can be easily adapted to different architectural variants and applied to models of different sizes. However, like most fusion methods, we also face limitations when it comes to combining networks of different depths. This is a common challenge due to the sequential layer-wise alignment inherent in most fusion methods. Despite this limitation, we believe it's an exciting research challenge to extend transformer fusion to networks of varying depths. In conclusion, we've demonstrated how separate independently trained transformer networks can be combined using optimal transport. We developed a novel algorithm for fusing multiple transformer networks that extends existing fusion techniques and caters specifically to the unique characteristics of the transformer architecture. We also discovered the benefits of using soft alignment when fusing transformers, a technique that has been underutilized in the past. Our technique retains most of the performance of the parent models in one shot and even outperforms them after fine-tuning, across multiple vision and NLP tasks. This proves the scalability and wide applicability of our methods, providing an efficient and promising alternative to ensembling. Our algorithm also successfully applies to the fusion of models of different sizes, efficiently transferring knowledge from larger to smaller transformers, offering an effective alternative to distillation. We would like to acknowledge the financial support from the Max Planck ETH Center for Learning Systems.